I am recording now. Yeah, okay. Okay, so this is the thing that where we stopped in our previous lectures. So there are two concepts for it. So the first one is a limit increment AK. Of course, when we talk about AK here is we have a sequence of set. And also we have a limit supremum of AK. So by the definition will be this. Yeah, so in a way, you can always assume when we talk about infimum of a set, that means we are talking about intersections. When we talk about supremums with respect to set, so we are talking about union. So likewise, so we have limit in supremum will be actually we can express it as infimum, supremum, AK. Okay, that's the way. So come back to this. So it might be a little bit complicated if you look at the symbol here. So there is involved two parameters, K and N over here. So it will be complicated. However, simpler ways to do it, so we can follow this procedure to compute this limit infimum for AK and limit supremum of AK. So what we can do is to compute maybe the first one, limit infimum. So what we can do is we can do this. So we can compute B1 to be A1 union A2 union A3 union A4 and so on. Okay. So similarly, we can construct B2. So begin with A2. Okay, and then we take the union for all the A. So likewise, we can have a B3. So we begin with A3 and then we take the union for all the A. Okay, so that's the way. So similarly, we can compute. I'm going to use this symbol C. So C1 to be, we just change the operation here. So C1 will be A1 intersection with A2 intersect A3, intersect A4, and so on. So C2 is A2 intersect A3, intersect A4, and so on. And C3 will be A3 intersect A4, and so on. So using this method, we can construct another two sequence of set B1, B2, B3, and so on, as well as C1, C2, C3, and so on. So once we have constructed these two sequence of set B, N, and Cn, then what we can use these two to compute our limit infimum and limit supremum. So we can use this. So limit supremum of AK will be, so this is a union. You can take notes of this. Okay, Bn, we are taking the union. Okay, then we're going to take the intersections for all the Bn, n from 1 to infinity. So if you don't want to use a shorthand here, which is just we are taking all the B and then we take the intersection for it. Okay, so you look at, we begin with union and follow with intersection. So this is how we compute the limit supremum for it. Likewise, we can compute the limit infimum. So what we can do is limit infimum of AK is equals to, we are taking union of all the Cn. So we C1 union C2 and so on. So just need to take note to compute our C. So we are taking all the intersection. And after that, this is become union and so on. So you may follow this procedure, just two steps. Step number one, calculating the sequence Bn or calculating the sequence Cn. Okay. And step two, using Bn and Cn, so we can identify, use it to calculate the limit supremum AK or limit infimum AK using these two formulas over here. Okay, so this is the thing for limit infimum. Okay, and next one will be the definition for limit. So, we are not going to use it. So this one, I don't think I need to write out here. So we just look at here. So we said that limit for AK is equal to A if and only if these two are identical. Limit infimum of AK equals to limit supremum of AK equals to A. So when these two are identical, we say that the limit exists, and which is equals to the set A. So we have two special case for it. The case number one, whereby we say this is an increasing sequence. That is, it satisfies this. So from here, you can see it getting larger and larger. A1 smaller than A2, and subset to A3, and so on. So that's why we can see the set AN getting larger and larger. So with this case, we said that this is an increasing sequence. So when we have an increasing sequence, so we can, for sure, the limit always exists. So that is just equals to the union of all the AK. Likewise, we can also have another special case, a decreasing sequence of set. That is, A1 contain A2, A2 contain A3, and so on. So you can see the set in a sense, it's getting smaller and smaller. So that's why we said it's a decreasing one. So for this kind of sequence of set, limits always exist. So which is just equals to the intersection of all of them. Okay. So this is an example. These are the examples that we have discussed in our previous lecture. So we just go to. I don't think we need to go through it anymore. Okay, so this is case one. So yeah, I think this is where we stop in our previous lectures here. Okay, before we proceed, go back to the definition once again. Okay. So limit infimum AK will be union intersections. Okay, that is actually the order should be we take the intersection first, K running from N to D, and then we're taking the union of all the N, and this is a limit supremum. Yeah. Okay, so alternately we can refer to here. So what's the meaning for this limit supremum AK? So this is means for all integer N, there exists a K larger than N such that the event AK happens. So in the terminology of probability, or we say this is infinity many, infinity often, sorry. Okay, so how is it? So you can see we can use the language of stat theory. Let's say we just begin with it. Let's say if we have omega, which is an outcome. So let's say it belongs to this limit supremum of AK. So by the definition, which is given by that, so that means omega belongs to intercept of this thing. Okay, so maybe I will follow this. Let's say I will just use a Bn, okay, and running from 1 to infinity. So from our construction, Bn is actually the union of all the AK, K running from N to infinity. Okay. So omega belongs to all this B1 and B2 and B3. So this is actually means that omega belongs to B1 and omega belongs to B2 and omega belongs to B3 and so on. Right? So this is in the, so if we use a simple language, that is omega belongs to Bn for all integer n. So that is the meaning for here. Okay, next we come back to this. What's the meaning for this B? Bn is the union of K running from N to infinity. So maybe this one. I put it over here. So what is our Bn? Bn is actually the union of AK, K running from N to N. So this is An union An plus 1 and so on. Okay, so this is true for all integer n. So omega belongs to An or An plus 1 and so on. That means omega must be belongs to one of the A n here. So this is just simply mean in the study omega belongs to AK for at least one K which is larger or equals to K, because it's one of it. Okay, so that is the, in mathematically, that's the meaning for to describe the element for limit superior of AK. So that means every element for this limit superior of AK is omega must be okay. That's the idea. Okay. For all n, so at least 1K larger than n, omega belongs to AK. So we don't know what is the value for n, but for sure we know that is 1n. So example, just it can be happen like this. Example, so when n equals to 1, so maybe omega will belongs to a. Okay, maybe just for n equals to 1, so we can find a k1 which is equal to 10. So that means omega belongs to a10. So again, let's say if we go further when n equals to 11. So for sure, we can get another k which is larger than this n, such that omega belongs to it. For example, let's say this is 98. Then omega belongs to a 98, and so on. So since this 98, then we have n equals to 99. Okay, then we can always get another k larger than this 99. Let's say maybe, okay, 101, such that omega larger than belongs to this number, and so on. Okay, so this process will never end, okay, and so on. So that is, I mean, if we want to describe this mathematically, that is the idea for it. So if we give a very simple example to demonstrate this idea, will be this. So for example, we can say this event. We just look at this event. A very simple event that can demonstrate this idea. So that is, how should I say? So it's raining. Let's say at particular, so 6 p.m. Okay, it is raining at 6 p.m. So we don't know which. For example, today, no, right? Today is not raining. So when n equals to 1, let's say 2 days. So today, so the answer is no. Okay, we don't know whether it's going to rain or not at 6 p.m. tomorrow. So n equals to 2, we don't know. Okay, we don't know. But I think I can safely say, although maybe tomorrow it might not be rain at 6 p.m. and also the day after tomorrow, it might not be rain at 6 p.m. tomorrow. But I think I can safely say that for sure, after 1 day, okay, after 1 day, it's going to be rain. So for example, maybe after 100 days, okay, so it's going to be raining at 6 p.m. Okay, so I'm just keep on waiting. So this definitely for some day it's going to happen, rain at this, okay, one time. And also, it's not going to stop because there's not only 1 day. So for sure, I don't know when, maybe some other days. Let's say 1,000, okay, at least, I don't know. It will be raining at 6 p.m. I'm not sure what is it. And this process will never stop. This is the one. Okay, so here, I mean, it will not end. Okay, just assume the end of the day won't happen. Okay? Assume our Earth will go and stay here ever and forever. Okay, so it won't end for sure. I just keep on waiting. There must be one day it's going to ring at 6 p.m. So this thing will not end. Okay, but the thing is, I don't know when it will happen. Okay, but at least for sure I know it will happen, but I don't know when it will happen. Okay, so that's why this is the one. So first of all, it will not be end. It will keep on happens and happens again. It's just that I don't know when it can happen. So that's why in this process we can also say this is IO. So that means it's infinity often. So that's why in a way we can also say that limit supreme of AK will be also say that AKIO. What's the meaning of IO here? It stands for infinity often. Okay, so that means the idea will be like this example or this phenomenon. So it will not be end for sure. It will happen and happen and happens again. So it might not be happen every day. Okay, however, I know for sure it will keep on happens and happens again. So that's why we can also say this limit supremum of AK will represent a phenomenon so-called infinity often. Yeah, this is one of the we can say the interpretation for this limit supremum of AK, right? So I hope you can get the ideas for it. Okay, so this is we can say an interpretation for limit supremum. We use infinity often. Okay, so the idea will be definitely it will happen and happens again, but it's just that we don't know when. Okay. Okay, for the next one, we can use a similar idea to look at this. Let's say we look at it. Omega belongs to limit increment of AK. So by our definitions, so this is union of all the n running from 1 to infinity, and k is n to infinity of AK. So if we, again, I think maybe I will just put this one as C, so that will be a better picture. So here, Cn will be intersection of k running from n to infinity. Okay. So omega belongs to the union of it. So I think you all said it. So that means at least. So this is just simply means at least 1n. So omega belongs to Cn. And Cn is this, the intersection of all this. So that means at least 1n, then this omega will belongs to all of them, A1 and an plus 1, and omega will belongs to an plus 2 and ever and forever. So maybe I'll put this one down here. That'd be a better idea. Okay, so now that is the ideas for it. I don't know what n is it, but at least 1n. And after that, omega will belongs to all the an onwards. Okay, so that's why this represent another phenomenon. So we call it ultimately or eventually. So that means eventually we can say that ultimately this omega will belongs to an for all the n plus 1, n plus 2, and n plus 3, and so on. Ultimately, for all these n, omega will belongs to all of them. So that means we can say that this event or this phenomenon will have, will be fixed already, so it will not be changed anymore. So that's why this will be represent a phenomenon, so-called ultimately. Okay. So a very simple example. So we can use a very simple example to demonstrate this picture. So for example, we have one guy, okay, a guy A, okay. So this guy A with his girlfriend, okay. So let's say a girl B, okay, a girlfriend B. So this B is his girlfriend. So maybe in day one, so let's say this A trying to propose to B. So whether B want to marry him or not. So in day one, so maybe you say A would say, maybe put it this way. So let's say A asks these questions. Would you marry me? Okay. So maybe in day one, so she said no. Okay. So that not happen. And then he asked again, day two. Ask again, would you marry me? So B answer no again. So maybe on day three, he proposed again. So the girl said no again. So maybe after 10 years, so days 3065. Okay. Finally, she said yes. Okay. So it doesn't matter. So maybe on all these are no. Once we say yes, right? Okay. Then in this day onwards, so 365 and so on. So A can say B. A can say that ultimately B is my wife ever and forever. Assuming they wouldn't die. Okay, and forever. So okay, this is one of the phenomenon that we can say so-called and ultimately. So the phenomenon that can which represented by this limit increment of AK. Okay, so I think later on, so we can have when we study the probability theory, so then we can have an idea this limit, the idea for limit supremum and limit increment for it. Okay, all right. So I think any questions?
Hi, Doctor.
Yeah.
I just want to ask: is for gamble rune, is it ultimate, often, or infinite?
For what?
For gamble rune, like if a gambler keep lose, it just keep sorry. If the gambler just keep gambling, eventually it will lose. Like, is that the ultimate event?
Okay, that one is we can't say unless you give me the probabilities of the games. Okay, the probability of game. So because we don't know what is the probabilities of a game, so I can't tell you this. Okay, so just for examples, because we don't know whether that's a fair games or not, right?
Okay, just assume it's a fair game and the probability is, and then if it just lose $1. If it win, then it just gain $1, and then eventually it will ruin. So is it like ultimate event?
So if you are talking about a non-fair game, right? So and the capital is finite.
Yeah.
Okay. So yeah, then it will be ultimately.
Okay.
Okay. So but it depends on the design of the game. Okay, we don't know for that. Okay. So if the game is a fair game, and there's a lot of constraint or the assumption, and if you assume, for example, if you assume the capital for the gamble is infinity, then it will never rule, right? So that's why it depends on how you design the game. So if you just ask me like this, so I can't answer you. So let's say if we assume the finite capital and assume it is not a fair game, yeah, I think ultimately, so it will lose all the capital.
Okay.
I think later on, I think when we do some actual calculation of the probability, then you can see these things. Yeah, but the idea is like this. Yeah, I hope now you can get the idea for this infinity optants, and we call it ultimately, and some of them call it eventually. Yeah, that's the idea for these two things.
One question is so if say you put a lot of gas particle in one box and eventually they will become equilibrium, is that infinite often event?
Okay, in that case, right, it depends on the situation. So let's say you put a lot of things, right? So at first it not stable. Okay, up and down, we don't know. But after a while, it will go to an equilibrium stage. So this one, that if you assume, then the state will not be changed anymore.
Yeah.
Okay, assuming the state equilibrium stage. So then this is actually belongs to the ultimately.
Oh, this is ultimately. It's not
ultimately. Yeah, ultimately is it will be stated that like this is the one, like for example, ultimately. So
just a question though, like if I change the k into time, isn't that infinite often? Like it keeps happening?
yes, but we don't know when.
Oh, okay.
We don't know when. So ultimately means after a while, okay, that means after n. So this n could be 100 or could be 1000. Okay, so that means after 100, so 100 and day 101, it happens. Day 102 and so on, it happens. This is ultimately. So I think a very good example will be this one. A better example will be this. So for example, you take a coin, you just toss a coin. Okay, so there are two, either head or tail, right? I think later on I'm going to talk about this, head or tail, right? Okay, so for sure, we cannot ensure whether you're going to get a head or tail, right? However, we can for one thing, if this is fair games, I think theoretically, assume this is a fair games, okay, a fair games. I mean theoretically, so when we say the event to get hit is sort of like will be infinity often, right? I think I can convince you, right? It is impossible you can get a tail forever and ever. Yeah, but we don't know when, right? It could be maybe the first 100 times we get tail, but the 101 times I get head, right? But after that, we don't know. It could be another 10,000 times I will get a tail in a row. We don't know. But nevertheless, I'm just keep on waiting patiently. One day we will get a head. So this is in a way, this is a phenomenon, and then we can reflect this phenomenon infinity often.
Understand. Thank you.
All right.
Hello, Professor.
Yep.
Hello. Just want to recall whether this distinction between infinitely often and ultimately, is it useful, for example, when we're talking about the weak versus the strong law somehow? Is that for the purpose?
Weak law and strong law. No,
Oh, okay.
no. I think it's weak law and strong law is talk about the convergence thing. So I think the only one that we can use, I think, is a Cantley lemma. Yeah, I think Cantley lemma. So this is not directly related to the weak law and strong law.
Oh, okay. Because I was thinking maybe I bring the wrong impression that, you know, when you say something about the weak law, you're just saying that it converges, but it's possible for it to happen infinitely often. But for the strong law, it says that ultimately there is an end beyond which there's no more violation of that.
It's not really like that. It's sort of like when you see strong law and weak law. If we have, I think later on. So now, in order to discuss all these precisely, so we need to set a lot of criterion. Okay.
Oh,
So,
okay.
but roughly to say that it's like the strong law is it just only tell you that if we just if put it this way, it's like the law of large number is like, I think this is a good example. You toss a coin. Okay, what is the probability of getting a head and what is the probability to getting a tail? Okay, so this one, unless I mean, if you just, let's say you toss it. Okay, okay, so maybe we look at it now. So to answer your question, which is for the strong law and weak law, so that is actually to explain or to convince this phenomenon. So we come back to this again. We toss a coin. Okay. So then there are two possibilities, right? Either we get a head or tail. And again, we assume fair game. We already. So now we ask the question: what is the chances to get a head and the chances to get a tail? So actually, we really don't know. For example, you make 100 times, maybe 1,000 times. Maybe you will get the number of head that you get will be 666, or maybe it will be it could be, let's say, 600, right? We don't know. It could be 600, and the number of tail only 400. So if you're judging by that, so you can, the probability for getting a head is 0.6. The probability of getting a tail is 0.4. Okay, and because of this number is not large enough, so this thing is not really reliable. So the only thing is, the strong law is that when n become very, very large, okay, then we believe the chances to getting a head and tail will be the same. But this is just theoretically, because we can never have infinitely many trials, right? We living in a finite world. I think our age is finite, so we cannot live ever and forever. So I think one day later, our universe will destroy. So that's why, however, theoretically, then we're using a strong law, then we can come up with this conclusion. So that is nothing to do with, I mean, not nothing to do. I mean, that is another story, not really directly related to this IO or ultimately.
Okay. All right.
Okay. So that one is used to, how should I formulate this? Can I say this theory or this formulation, something like that? Okay.
Dr. Lu, I have another question. So just want to link what you taught last week and just today. So we learned how to compute limit supremum and limit infimum. So are you saying that once we are able to determine the limit infimum or limit supremum of a sequence of set, then therefore the limit infimum and limit supremum will have these properties?
Okay.
Is that why? It's because you're saying that limit supremum, if for example, if limit infimum, it means that for limit supremum, it means that there's infinitely many events AK happen, right? So, and we learned last week how to determine what a limit supremum is. So does it follow from that? Is the knowledge like that such that, okay, we know what is what's the limit supremum, therefore there's infinitely many events AK can happen. Is that the logic of things?
Okay, one is the technical part, right?
Mm-hmm.
Maybe I can put it this way. One is the theory part. Technical part is how we use mathematical technique, the set theory, to perform the calculations, right? Okay, we can use the math to establish the theory and all those mathematical properties for all these concepts. Okay, and after that, then we can see how are we going to interpret this kind of abstract concept. That's the way. Okay, maybe one way is we can use this to describe. We can use a limit supremum and limit infimum to describe this kind of phenomenon. Okay.
I see. So it's a description of, it's a mathematical description of infinitely often and ultimately.
How should I say it? Yeah, in a way you can say that, but it should be the other way around. Okay. First of all, we have something that is a mathematical concept. Okay. And after that, how are we going to use this kind of concept to describe these things? I think, how should I? Yeah, I think maybe it's like that. For example, sorry, I think actually I'm not. My major is not in statistics. Okay, so that's why I can say I know nothing about the application of statistics and all these things. Yeah. So what I can tell is things in the physics maybe put in this way. So I think for example, that's something like, okay, for example, in our nature, we have something so-called a very abstract. There's some phenomena. We have the so-called electromagnetic, right? We can observe this kind of phenomenon. For example, you take two magnets, okay, and then you can see it will attract or things like that, right? So we can see this electromagnetic, the phenomenon, okay? So how are we going to describe this kind of phenomenon using mathematics? So then we use a calculus, or we can something so-called the concept of vector to describe this thing. Okay, so that's why it should be the other way around. It's sort of like, first of all, we can have the phenomenon of I/O, okay, by observations. Okay, we can have this kind of phenomenon, or we can have the phenomena of ultimately. Okay, then we can use this set theory idea to describe or represent this thing. Okay, that's the ideas for it.
Understand. Okay. All right.
So in a way, it's sort of like just imagine you can put it this way, math is a language or some kind of symbol for us to describe some phenomenon. Okay, for example, you look at these things. So
in other words, So in other words, we are saying that if we know a certain phenomena is infinitely often or ultimately, then we can describe it in terms of limit supremum and limit infimum.
Yes.
Okay.
Yes, exactly. Something like that. So I think this is something like that. So I know in our nature we have this object, right? So if we want to study this object, we have to use some kind of symbol or some kind of our language to describe it. So we decide to describe this using this fish. Okay, that is easiest for us to have a discussion. It's more convenient if we have a common language to describe this thing. So we use this like that. So it's something like that. Okay.
Understand.
Okay. Okay, where am I now? Oh, okay. So I think at least hopefully, I hope you can get some idea for it. So at least you have the idea what is the infinite often and ultimately. So why it can be, why these two phenomenon could be described or depicted by these two ideas, limit supremum and limit infimum. So that is actually, you can see using the set theory ideas like this. Okay, then we can have these kind of things. Right. Okay, so okay, let's proceed with the next chapter. Okay. Okay, maybe we start. Okay, probability space. Do I need to go through this? Okay, so I think just briefly go through these things. Just a very okay, I think this is quite straightforward. Okay, first thing first, I believe you guys know what is meaning by random, right? So random, in a way, is sort of like something that's uncertain. Okay, we cannot for sure what is going to happen, right? Okay. And also, I believe you know the meaning of deterministic. Okay, deterministic is something like it's sort of like for sure it will happen. Okay, so yeah, I think this is a good example. So random phenomenon is we are tossing a coin. Okay, so assuming we are not cheating, it's a fair experiment. So that means we do not know whether we will get head or tail. Okay. So, and number of customers that arrive at the bank. Okay, again, we do not know. Okay, we cannot for sure how many of them. Yeah. So, phenomenon, deterministics, right? Something for sure happens. Okay, I think it's a very simple example. Is the sun is rising from the east. So I think this is okay. This is deterministic, right? As long as our Earth is still here, so everything is follow this kind of the evolution, the rotation. So then the sun is rising from it. So that means this is something deterministic, right? So that's it. Okay. Okay. So next will be this. An experiment is usually conceptualized, so and might not correspond to a real experiment. So here, we always thought experiment. Okay, so that means we just imagine we can do this kind of experiment. So we are not really doing the actual experiment for it. Okay, just have this idea for it. Okay, so for example, we can toss a coin, so we can only have two possible outcome, head or tail. Okay, again, we assume everything conditions are fair and so we don't have to worry about it. Okay, so okay, next will be this outcome. Outcome will be the result of an experiment. So this is the term. Okay, maybe this one is important. I think maybe I should write down one. So I suppose you understand what's the meaning of random experiments. Okay, you get an idea. Okay, a random experiment. So that means that is a process that we can repeat and so on. Okay, and we set all the conditions. Okay, first thing. So then outcome. So that is a result of a random experiment. Okay, so that is an outcome. Okay, next. This is the idea for you. Okay. Okay, so we understand the meaning for this random experiment, and we know the terms of this outcome. Okay, now we want to study this random experiment. Okay, So to study this random experiment using mathematical formulations, so what we can do is we model this with something so-called the probability space. That is, all the elements inside this random experiment, we try to use some mathematical object to represent it. So this one is a mathematical model for this random experiment. So once we use some mathematical object to represent the elements for this random experiment, then we can use the theory or the formula of math, and then we try to establish some kind of study of this or the theory for this random experiment. Okay, that is the idea for it. Yeah. Okay, so then we have to know what are the elements for this probability space. So from here, we know that if we have a random variable, so the main thing will be the outcome. Outcome will be one of the possible, I think maybe we should say, possible result of a random experiment. Okay. So then for this, then we can have three important elements here. So number one, the sample space. Okay, so we use a symbol omega. Okay, what is a sample space? Sample space will be we gather all the outcome. Okay, a sample space will be the collection or the class of all the outcome, the set of all outcome, possible set of all possible outcome for it. So this is the first thing. Okay, once we have established it, then the next thing will be this. We have another element, then we simply call it a sigma field. Okay, what is a sigma field? Okay, so we represent this by script F here. So this sigma field will be the collection of all events. Okay, then we have to know what is the meaning for an event here. Okay, outcome, I think we all understand or we agree. An outcome means a possible result for an random experiment. And what's the meaning of events here? Roughly speaking, we can say an event is a collection of certain outcome. Okay, an event is a collection of certain outcomes. So that means if you use the language of mathematics, so a collection of certain outcomes, so which means this event is a subset of omega. Right? So that means we can assume one outcome to be one element of this capital omega. Another outcome will be another element for this sample space, capital omega. So an event is, roughly speaking, is a collection of certain outcome. That means it's a subset of this omega. And it's not all the subsets. So there is we need one restriction here. There is here. An event is certain kind of subset in a sample space that can be assigned probability. So later on, we're going to look at it. So we just give an idea. It's a collection of certain outcome. So that means it's a subset of omega, which we can assign a probability. Okay, so up to this point, so we are using our layman language. Okay, so I believe you guys have some idea what is meant by a probabilities, right? So later on we're going to talk about the actual meaning for probability. Okay, so that is the meaning of event. So a certain kind of subset of outcome. So we can say this is a subset of omega, which we can assign a probability. So if we cannot assign a probability for this subset, then we cannot say this is an event. Okay. So the second thing would be okay, and also finally, then we have the third one. That is, we must have a probability P. Right, so that is our mathematical model or mathematical formulation for random experiment. Then we use this model, this formulation, so-called a probability space. And there are three important elements in a probability space. First one will be a sample space, meaning that all the possible outcomes, something so-called sigma field. Okay, that means this is a collection of all the events. Okay, and finally, we must have an operator or something we can assign probability to each of the events here. So three elements for it. So at least now you have some idea. A probability space consists of these three elements here. Okay, later on, we're going to look at what is the actual mathematical meaning for these three objects. So that will be some kind of the abstract definitions.
Dr. Lu, a question.
Yeah.
Is if this question answered later, you can just say that. But why is the constraint of can be assigned probabilities is for events and not for the sample space? You know, like why don't we just exclude that at the sample space level, but we only put the constraint on at the event level?
Come again?
Because you're saying that events is a collection of outcomes which we can assign a probability.
Yes.
So that means for events that we cannot, for outcomes that we cannot assign probability, it's not an event, right? But,
no. Okay, never mind. So no, it's like this, one by one. Okay, yeah, I got your question. I'm going to answer your question later. Okay.
Okay.
But just to make it clear again, sir. Okay, first of all, sample space, I think it's clear, all the outcome. Okay, all the possible outcome. And sigma field is all the events. Later on, just have some idea, something we so-called event. What is an event? I think I better put it here. I better put it clearly. Is a special types of collection of it. Okay, maybe it's a special types. It's a special types of subset in here. Okay, so which means an event you put in, you can at this stage you can imagine, just remember an event is a subset of omega. Okay, but we can have a subset which is not event. So that is later the story we're going to discuss later. Okay, so that's the event for it. Okay, I'm going to do it slowly, step by step, to explain to you guys how to choose something, or how to determine when something is so-called event and when it is not an event. Okay, we're going to discuss it step by step, right? Okay, so I think
sorry, doctor.
Yep.
Yeah, I want to ask about the sigma field, right?
Mm-hmm.
Is it like a collection of all possible events for the experiment?
Yes.
So like let's say I toss a coin 5 times, so a sigma field will contain events like getting hit once, getting hit twice, something like that, is it?
Yes, but okay, be patient. I'm going to describe it slowly, one by one.
Okay.
All right.
Okay.
Okay. So that is what we're going to discuss, right? Okay. Don't worry. Here actually, this is just a rough idea. I just give you an idea what are all these things. Okay. Later on, I'm going to go through the actual definition one by one. Because the reason is here. This is from my experience. Okay. I don't know your background, so I know some of you guys' background is not from mathematics. Some of you might be from just engineering or what. Okay. So your training in mathematics might not be that substantial. Okay. So that's why if I directly go to those are very abstract kind of a discussion of mathematics, I'm just worried that most of you guys cannot follow. Okay. So I think I just want to do it slowly like this. Okay. So at least I just let you know we have something like that. Okay. These three things. Okay. Later on, I'm going to do it slowly. What is the actual meaning for these three things? Okay. You have to fulfill certain kind of the criteria, right? Mathematical criteria to do it. Yeah. It's 7 o'clock. By the way, when will be our? Oh, okay, no, 7:30, right? Okay, yeah, we still have half an hour. Okay, so I think I just carry on. Okay, so one thing, this one, a concept, an event is a subset in the sample space whose probability is defined. Okay, so forget about this one first. And also forget about this one first, sigma field. Okay, I'm going to come back to this later. Okay, again, this one I'm going to come back this later. Okay, maybe I directly come to this one first. Okay, again, this one I come back later. Okay. Okay, let's come to this. We begin with this one. Okay. So again, I repeat again. So we're going to construct these three objects: sample space, sigma field, and the probability to describe one random experiment. Okay. Okay, so I think this is the answer for your question just now. What is the sigma field? Actually, the definition is here. Okay, let's forget it first. This one, definition for probability. So we leave it first. Okay, we come to this. Okay, here we're going to consider different kind of probability space. So there is omega, f, and p. So it depends on whether the sample space is these three cases. Okay, so I will going to begin with the easy one. Okay, so first I start with easy one. So this one means the omega is finite. Okay, and after that we go to the intermediate case. Okay, whereby omega is infinitely countable. So that means is discrete but infinite. Okay, and finally, so this is the hard one. So whereby omega is uncountable. So that means it's a non-discrete case. Okay, so based on the nature of omega, so that we can use different method to construct, to construct the probability space. Okay, so we start up with the easy one, follow with the intermediate one, and then finally we come to the hard one. So then we can look at a general way to do it. Okay, so let's begin with the simple case. By the way, do I need to give you an example for this? Okay, so maybe a very simple example, I think first. So let's say we look at this experiment. We toss a coin. Okay, let's look at this a simple example. We toss a coin. So then how many possible outcomes? So I think we know it's either head or tail, right? So that means in this case, our omega is either head or tail. So this is the first case. So this one is finite. Okay, So another example is, I think you roll a dice. Okay, the possible outcome are 1, 2, 3, 4, 5, 6. Okay, another example of finite case. Okay, so this is at least you have some idea, an example for it. So finite case. So how about this one? So we can look at these examples. I think I had mentioned this just now. We toss a coin until we get an head. Okay, so we are concerned with the number of tosses to get an head. Okay, so we look at it. So that means we have how many possible outcomes here. So if we consider outcome with number of tosses in order to get an head. So that means it is possible, n could be 1, right? So that means we are so lucky. The first try we get, we already get a head, okay? And also if you are not so lucky, first we get a tail, then we get a head. And, or it can be, we get a tail, head, right? Yeah, although although we know eventually, sometime we should get a head, but theoretically, this process might be up to infinity, right? So that means in this case, you can see our omega will be 1, 2, 3, 4, 5, 6, 7, and so on, because we don't know it can be up to 1,000 times before we will get 1,000 tail before we get a head. Okay, so this is up to infinity. So that's why in this case, then we have an example, omega is discrete, but infinite. Okay, so this is for the second case here. Okay, for the third case, omega is uncountable. So that means it is not discrete. So a very simple example would be like that. So just imagine, let's say we have a wall here. Okay, we have a wall here. Okay, maybe forget about wall. Okay. Okay, let's say we have a field here. So just look at this example. So we take a ball, okay, and then we throw the ball. Okay, we throw a ball. So then we measure the distance from here. Measure the distance from here. Okay, just imagine we have a very accurate gauge or measurement. So we can measure until 0.000000000000000 meter. Okay, so that means you can see this case, actually it can be the measurement is not discrete. For example, our x could be 1.00567. Imagine if we have a very accurate ruler or gauge, then we can have things like that, meter, right? So in fact, this could be never end. Okay, so we can see in this case, if we throw a ball from here, so we are interested on the distance that we measure our position and where the ball fell down here. Okay, then in this case, then we can see in our omega could be any numbers. So x greater or equals to 0. Yeah, greater or okay, greater than 0. Greater than equal could be this like that, right? So that means in this case, so this is a case which is non-discrete. Okay, so based on the nature for this omega, so we split into 3 different cases. Okay, we see how to construct the probability space for these 3 cases one by one. We start off with the easy one when omega is finite. Then it's very easy to construct. and follow with this. And finally, we look at the hard case here. Okay.
Sorry, doctor.
Yep.
Yeah, I want to ask, like, let's say, for example, I toss a coin 1,000 times, right? Is the sample space considered as finite or infinitely countable?
Depends on what are you interested in. For example, you toss a coin for 1,000 times, right? So if you want to record the 1,000 times, let's say 5 times, okay?
Yeah.
It's the same. Let's say you toss a coin for 5 times. You want to record down what is the possible outcome for these 5 times, right?
Yeah.
So that means it can be, for example, okay, so just example. So let's say, make it easy, you toss a coin. You have to look at what are the possible outcome that you're interested. Toss a coin 5 times. Okay, so you are interested on what are the result that I don't use outcome for each toss. Okay, you're interested on what are the results for each toss. So that means in this case, right, you're going to have 5 different. For example, you can have omega is head, right? Yes. So this is one possible outcome. Another possible outcome is head, tail, head, tail, head, and so on, right? So that means in this case will be your omega will be 5 of them. So you can see is let's say I don't use maybe omega is this. So you can use this is omega 1, omega 2, omega 3, omega 4, and omega 5. So this so omega I will be either head or tail. So here I think you can easily count, right? How many possible outcomes that you can have. So I think the number of will be 2 power of 5. Right? So for sure, this is finite because it's always less than infinity. So that's why this is a finite case. So in this case, this is a finite one. So even if you put this is 1,000, okay, if you change to 1,000 here, it doesn't matter. So even if you change this to 1,000, what is the number of possible outcome is just 2 power of 1,000. Although it's a large number, but which is still finite. So in this case, we consider this is a finite case, right? Okay, so actually, it really depends on what phenomenon you are interested in. Okay, so that is the case for that. Okay. All right. Okay, so let's look at it. How to formulate this probability space. Again, let's forget about definition 1.1.2 and definition 1.1.1 first. Okay. Okay, we directly look at how to construct these things. Okay. Okay, so when we have a finite sample space, so supposing we have omega 1, omega 2 up to omega n, so that means n of them. Okay. So first, how to choose our sigma field? Okay, the easy case is we just simply in under this case, we just simply take our sigma field to be the power set of omega. So this one, okay. So okay, so maybe I do it one by one. So so when omega is omega 1, omega 2 up to omega n, so this is a finite case. So we just take our, so this is the power set. So this is I mean the collection of all subset of omega. Okay, so For finite case, you don't have to worry about the what kind of event, what kind of subset cannot be event. So we can just simply take all the subset. So that means for finite case, all subset will be an event. So this one, all subsets of omega are event. Okay, so in this case, you don't have to worry about it. So everything will be event. Okay, so standby. Okay, step number 2. We construct a rational probability function. Okay, rational means based on some kind of our common sense or some method, okay, which is an acceptable method. So we construct P omega 1, P omega 2, and P omega 1. So that means for each of the outcome, so we assign a value. So which have to fulfill this. P of omega k must be in between 0 to 1. And we sum all this is equals to 1. Okay, so that's the way. I think it's easy. And 3, we just define our probability to be, let's say we have A is a subset. So PA will be, we just summing up all the P omega, where omega belongs to A. So that's the way to construct our probability space. Okay. First of all, I think this is clear. This omega, okay, capital omega, this is depends on your experiment. So this one you can determine by the experiment. Okay, depends on your experiment. So you can always identify your omega. Okay, so this one first, this one we can fix it, or we for sure we know based on the experiment. Okay, based on this omega, then we can construct our sigma field. Once we construct our sigma field, then secondly, what we can do is we just construct, make sure it fulfill this. P of omega k will be in between 0 to 1. And after that, the sum of them, P omega 1 plus P omega 2 up to P omega n must be equals to 1. Okay, number 3, we leave it first. Okay. So using this way, then we can sure this is we can construct a probability space for it. Okay, later on, we skip this one first. Okay, okay, just follow this 3 procedure. Then we construct our we use this 3 procedure to construct our sample space for it. Okay. Okay, we will come back all this later. Okay. Okay, let's look at our examples. One point 1.3. So has to be a suitable probability space for each of the following randoms experiment. Yeah. So we look at the first one. Fair coins is tossed once. Okay, yeah, depends on it. So we toss once. Okay, so then first one. So I think this one is clear. You can see our omega will be either head or tail. Okay, so A, we can get it. Okay, B. Follow our standard scheme here, how to construct our sigma field. So we just take our sigma field to be the power set of omega. So in this case, so the sigma field will be the power set of omega. So that means this is, we consider all the possible subset. So that is empty set, the set with only one element H, the subset with another element T, and finally H of T. So that is our omega. So this is our F. So we got our sigma field. And C, construct a rational probability functions. So I think what we can do is we assume this is a fair game. So that's why we can assume P of H is 0.5 and P of T is also 0.5. Okay. So we construct these two. Next, we need to make sure it fulfills these two properties. I think it's clear. So clearly, this 2 is in between 0 to 1, and P of H plus P of T is equals to 1. Okay, so we can see, right? Hence, we can say the equation 1.1 is fulfilled. Okay, so once we can construct this, I think this is clear already. We can define our probability to be like this. P of A will be summing up the probability for each of the value here. So I think maybe I can state this. So in this case, then we can see the probability measure can be described by using this table. So we can be empty set, H, and T, and omega. So what is our PA? So for this example, empty set is always 0. So H, we can follow only one element. So this is 0.5, this is 0.5. Omega actually consists of 2 of them, right? H and T. So that's why it's 0.5 plus 0.5. So that is 1. So this is, okay, we can describe the probability measure by using this simple table here. Okay, so I think it's quite straightforward. Okay, quite easy for us to construct a probability space for a finite sample space. Okay. Okay, so for the next example, I think it's here already. So we look at the second example. An arm contains 3 red balls. Okay, so the number of red ball is 3. So the number of white ball 2. The number of blue is 5. Okay, so 1 ball is selected at random from the arms. Okay, so in this case, so we are consider we select 1 ball from here. Then we are interested what color is it. Okay, so that means in this case, so I think we can have this is either red, white, or blue. So B. So this is a bit longer. So we have 3 of them, right? So in this case, the number of, not this one. This is 3, right? So that means in this case, the number of our sigma field is 2 power 3 will be 8 of them, because I have 3 of them. Okay. So we can take F to be the power subset. The power set. So since I have 3 elements, so that means will be 8 of them. So the empty set, the one with R, the singleton with W, and then with B, and then we also have R and W, R and B, and W and B, and finally we have our omega, which is with 3 elements here. Okay, 3C. So we want to construct a rational probability value for each of the outcome here. So I think based on here is quite natural. We can set P of R to be 0.3, okay, and P of W is 0.2, and P of B to be 0.5. So I think this is quite natural, right? And I think it's acceptable. We based on the frequency of it. So next, we need to verify, make sure it fulfills these properties here. Okay. So then I think it's clear. So we can check clearly. All these are between 0 to 1. For omega equals to R, W, and B. Okay, they're the same. And also, we have to make sure if we summing all the number, we give 1. So we can see PR plus P of W plus P of B is equals to 1. So hence, we can see the criterion 1.1 is fulfilled. Okay, so once this is fulfilled, okay, then this is a probability measure for it. Okay, and number 3, we define a probability measure as this way. Do I need to write down? Okay, maybe I can write down this. So in this case, so I'm running out of space here. Okay, I just put R. So and then I have a W. I have a B. R W. WB. RB and this. Okay. So I think we can easily construct this. This is always 0. So this is 0.3. This is 0.2. This is 0.5. Okay, RW. So we summing up these two. That will be 0.8. I think no problem. You can get it. WB will be we summing up 0.7. RB. So we get 0.8. So we sum of them 1. Okay, so we can easily get this is the probability measure for it. However, we don't have to list this thing out because once we are able to construct the probability function for each of the finite outcome, then automatically this will be a probability measure. Okay.
Professor, sorry, just want to ask the interpretation. The RW means you get either or if you toss twice, right?
What?
What is the event RW? It's not for one single event, right? Because you just take one ball.
Oh, okay. Okay. The event is like when we put R, right? So that means the ball that we pick is red color. So that means this one means RW means the event where the selected ball is either red or white. Okay, it is either red or white.
Okay.
Okay. So actually, in general, we can follow this standard method to, I mean, just look at this example 1.1.5. Okay, in general, for a finite sample space, we can always follow this standard scheme to do it. Okay, that is, let's say our omega has n outcome, omega 1 up to omega n. Okay, so this is a finite case. Okay, so this is a finite. Okay, so if this is finite, so we can always select the sigma field to be the power set. So that means all the events, all the subset will be event. So next we can, I think this is a quite natural, right? So we can take the frequency as it. So P omega 1, so will be equals to this. So actually, these two examples, we are following these methods here to do it. I think this is also follow the same, right? Oh, okay. Okay, so it's about 7:30 now. I think, yeah, it's good time. So for us to stop now. So as usual, let's take about 30 minutes break. Okay, so we carry on our second section at 8 p.m. Okay.